Hi there, Science 9. So today you're going to be looking at diatomic elements and covalent network crystals. This is lesson 9 from your Chem Notes package. Just working towards the end of the unit there. There's no assignment I'm adding with this for any kind of future quizzes. There's a good chance it'll show up there though. So two topics that are of interest here. One is how do solids bond together in a molecular way. What are some other ways that you might not have seen? And also how gases of pure elements behave in nature. Probably the best way to start is with what I think in some ways is one of the coolest aspects of chemistry and earth science is this concept of a covalent network crystal. These are found for pure nonmetals, but they're also seen with metals. The key thing with covalent network crystals is that the bonds are not ionic, they're covalent. So what does that mean? For an ionic bond you've already looked at, they exist because of ions being in a kind of a very arranged in a crystal lattice where the positive ions are as close as they can get to the negative ions and as far as they can get from other positive ions. And the negative ions, same thing, as far as they can get from other negative ions, as close as possible to the positive ions. So they're packed together in that very particular way that maximizes the distance between same charges and minimizes the distance between opposite charges. They're stacked. The simplest example that's often given in textbooks is for salt, table salt, sodium chloride, where the ions are stacked together like a cube, which matches perfectly the shape of a single grain of salt that you would see if you looked at it through, say, a magnifying glass. Covalent network crystals are different. The bonds are not ionic. The atoms that are involved do not have a charge. They're sharing electrons. So you don't have atoms that have just taken electrons, atoms that have given electrons. You have atoms that are sharing electrons with the atoms next to them. What you actually are finding, what you're forming when you make these crystals, this is a little counterintuitive. You're basically making giant molecules. You're used to thinking of molecules as, say, a molecule of sugar is ridiculously small. We can't image it directly. It's only indirect evidence that tells us what the structure is of, say, a sugar molecule or a molecule of gasoline or water, for example. Covalent network crystals are giant molecules. And by giant, I mean large enough that you can hold in your hand. But it's still one molecule because all the atoms are bonded together in a continuous crystal network. The simplest example that's often given as a textbook example is the diamond. So here is a representation of a carbon atom. You've probably heard that diamonds are made of pure carbon. You know, you might have heard that if you were to take a diamond, you can actually burn it at a high enough temperature that you can make diamonds out of, like, by compressing coal or pure carbon. I don't know about the exact ways that diamonds are made on the earth, but they are made of pure carbon. Each carbon atom has got 4 electrons that it can bond with other atoms. It doesn't only bond with carbon atoms, it can bond with any number of different atoms as long as it's sharing. It's sharing those electrons. It doesn't give all its electrons away. It doesn't take on 4 electrons. It shares. Also, when it shares, it's trying to keep its electrons away from other electrons and also in a way that basically sticks them off from each other and maximizing the spacing between the electrons that are orbiting the atom. So what does that look like here? This ball again represents a carbon atom. Notice there, you can see 3 of the 4 holes, and then if I turn it over, 1. You have up, and then you have this way, and backwards is the direction that those electrons are sticking out from the atom. This is going to form what's called a single bond. Here's a little representation of that as well. It looks a little bit like those traffic spikes that police will use when they want to stop a vehicle. It's extremely stable as a structure. You also know that you probably know that triangles are a very stable structure in architecture. It's seen at this atomic level as well in the case of a carbon atom. Now, what's really cool about this is this leads to one way that carbon atoms can join together and form a covalent network crystal. In fact, it's, I think, in a lot of ways the simplest way, and it's also the strongest way. What I've done here is I've taken a whole bunch of those molecular model building kit carbon atoms, right? Each of them will have space for bonding with 4 electrons. Now, there is a such thing as a double bond where 2 pairs of electrons are shared rather than 1 pair of electrons, because each of these will be 1 pair of shared electrons, but we'll get into double bonds later. Here we're looking at just single bonds. Each of these bonds here in this crazy structure I've made that represents a diamond molecule, a diamond crystal, is a single pair of electrons. I want you to notice some things about it. First of all, there, flat across one plane. You probably have known of, or you may have heard about diamond, like jewelry makers, people who make diamonds into rings. You may have noticed that with diamonds, you get these nice flat faces. That's explained at the atomic level. What you're seeing there is an edge of a crystal. Look at that, this flat crystal face right here. Something else that's really cool about this. Well, for a start, try to see one of these atoms, maybe this one right here in the middle, okay? What I'm pointing at, my finger's on it. How's that working out? There, that one right there in the middle. Notice that it's bonded, singly bonded to 4 different carbon atoms that are around it, okay? So that's what I'm talking about. Each one of these here is going to be bonding to exactly 1 other carbon atom, forming this structure. Also, notice this, the really cool aspects of it. Look at that, how you can see through there. It's symmetrical in all possible orientations. However I rotate it, I get that symmetry. Hey, also, by the way, notice that symmetry. If you look at it, look at this face right here. There, there, here, 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 and here. See that? Facing the camera here, we've got a kind of a hexagon. See that shape right there? There's a hexagon. So it's arranged with these, each one joined to 4, and then you have a higher level arrangement where you've got these hexagons. This is really stable. So see this right here? I can drop this. I can drop this on the floor. I won't throw it from the ceiling, but I could. When I make molecular models with bunches of other atoms, like, say, an example of a sugar molecule, if I were to do that and drop it on the floor, it would change the shape of it. When I dropped this on the floor, it didn't change the shape. The structure of a diamond crystal, again, because this represents a diamond crystal, is extremely stable, solid, and strong. No single carbon atom is taking all of the weight, and it doesn't have any capacity. If I try twisting it, It doesn't have a capacity to rotate. You can't twist a carbon atom in the same way. You can't twist a diamond crystal in the same way that you can twist many other molecules. It's stable, it's rigid, and it's strong. Now, diamond is not the only covalent network crystal. There are many other examples of this. Here, have a look at that. See that? All the hexagons there? There are many much more common examples in nature. Something you've probably seen is this, okay? Very nice. It's the best crystal I could find in our collection here at the school. That's a much more common crystal, but it shares in common with the diamond that it's a covalent network crystal. Most of you will probably already know from looking at it that you were just looking at a quartz crystal. Quartz crystals can grow to be incredibly large. A pure quartz crystal will be clear, transparent. In the same way, you have a covalent network of bonds in a quartz crystal, such that each crystal, as long as it doesn't have, say, cracks in it, which they can get, is a single molecule. Chemically, because there's a network of bonds. The elements that are involved there are not carbon. There's no carbon in a quartz crystal. Quartz crystals are made of two elements, silicon and oxygen. In fact, for every single silicon atom in a quartz crystal, there are two oxygen atoms. So what's called the molecular formula is silicon dioxide, SiO2. You're going to learn more about what chemical formulas mean, but what I'm telling you now is that it's got the elements silicon and oxygen, and that for every silicon atom, there are two oxygen atoms. So silicon dioxide for two oxygens. In the same way that CO2, which you've heard of, has got one carbon atom and two oxygen atoms in it. Here, though, unlike for CO2, it's in the form of a giant crystal, a giant molecule. I have some notes to go with today. You can pause the video, write them down. In some ways, I guess I added little bits of information, little nuggets of information you might not have seen elsewhere. So a covalent network crystal is formed by atoms joined in covalent bonds. They're often formed from nonmetals, although here you're violating some of what you might have expected so far. You might have expected, oh yeah, if you got a metal, for sure, it gives away its electrons. Because, yeah, when metals react to form simple chemical compounds with nonmetals, very often they're giving away electrons. Very often then, they're becoming ions. But many of the most common minerals in nature that you find in a rock have got metals in them. Aluminum is found in a lot. Magnesium is found in a lot of them. Iron. The most common elements on Earth, I should say, are found in all kinds of crazy arrangements inside minerals. To be clear, if you ever get into geology, there's a distinction we have to make here between, say, a rock, which is made of a mixture of different minerals, and a mineral itself, which is a pure chemical compound. If you find, say, a piece of granite by the side of the river, you'll notice it's got lots of speckles in it. If you were to shatter it, you would see that the speckles shine, they sparkle, because what a granite rock is made of is actually individual minerals. Quartz, for example, is a mineral you find in granite, and those crystals that are in the granite, those minerals, are covalent network crystals. The atoms are bonded covalently. In that case, as far as I know, they're nonmetals, though I could be wrong on that point. The point is that in minerals you can get metals that are bonded covalently. Now, the next topic of what you need to learn, and this is a more important thing, so maybe pause the video here and write this down here. And I also am going to do the same thing for a sheet that I drew up for you. and explain a bit about what it all means. This didn't fit very well on the whiteboard, so I did it here. Very often in chemistry, you're going to be working with what are called diatomic elements. Now, I've taught you that the atom for helium, and that for neon, that for argon, they're chemically stable. They don't need to bond with anything else. In fact, any compound made with a noble gas is actually extremely unstable. Noble gases are atoms of noble gases are far happier on their own. They don't need to form chemical bonds with anything else. But there are many exceptions to, this is not true for all atoms, is what I'm trying to say. Many compounds or many elements, single atoms of them, are not stable. So instead, if there's no other element around for them to form a bond with, they bond with themselves. This is true for nonmetals. Metals don't behave in this way. Nonmetals do. I bring this up now because, unlike with covalent network crystals, for this issue of diatomic elements, you're going to see this a lot. Going forward into Science 10, Chemistry 11, diatomic elements are going to come up a lot, so you should know which they are. They surround you. The diatomic elements that are in, they actually make up the majority of the air around us. Nitrogen and oxygen, they form gases. Most diatomic elements form gases quite easily, and they make up a big chunk of the atmosphere. In fact, nitrogen is something like 75%, oxygen is about 21% in the air. Collectively, they're well over 90% of the air is diatomic elements. So when we talk about the element, oxygen, in nature, we don't say O, we put O2. We don't say N for nitrogen, we say N2. This is because in the pure element, oxygen, as it's found in nature, it's made out of pairs of oxygen atoms. And those pairs are bonded with covalent bonds. The electrons are shared. Why wouldn't they be? One oxygen atom versus another oxygen atom, you're not going to have a situation where one has more pull for electrons than another. They have an equal pull for electrons, and so they share. They share electrons. Now, the ones that you should know, you should be familiar with, are hydrogen, oxygen, nitrogen, and any of what are called the halogens. So you know Group 18 is the noble gases, helium, neon, argon. Group 17 is the halogens, those colorful, nasty chemical elements that react so strongly with everything else. As pure elements, they are diatomic. Fluorine is F2, pairs of fluorine atoms. Chlorine is Cl2. It exists in nature as pairs of chlorine atoms. I want to get to the Bohr diagrams I drew for you. So let's walk through that a bit. Let's look at the top left one right here. That's a Bohr diagram for a hydrogen atom. Now I've shown you Bohr diagrams for a hydrogen molecule. I've shown you Bohr diagrams for hydrogen atoms, and I showed you, and here's an H, then we had a circle around it, then we had two dots, and I told you those dots are the electrons of hydrogen, and because they're the only electrons, they're the valence electrons. In fact, of course, a hydrogen atom has just one electron. Here what's happening is, again, each hydrogen atom has just one electron. They're having one each. A hydrogen atom here is bonded to one here. Think of it as this one here had that one, and then this one right here had that one, and they kind of clicked together and formed a bond made out of two electrons, because chemical bonds are made out of pairs of electrons. Oxygen, fluorine, chlorine, they can all behave the same way, or at least in a very similar way. Fluorine is the one I next give an example of. The inner electrons, those first shell electrons made out of 2 electrons filled with when they're at 2, they're not involved here. It's the next shell, those valence electrons that are involved in making that bond that is a diatomic element, forms a diatomic element. So what we see is that fluorine has got 7 valence electrons, and here where I'm putting my finger, it's the same deal. A lone valence electron is clicking in with another one, and we're making a pair. This gives the fluorine that noble gas stability that the atoms want to have. They get that noble gas stability by sharing electrons with each other. Now, fluorine gas, if you put it in contact with pretty much everything else, the fluorine molecules split apart and bond with the other elements. But on their own, stored as a pure sample, fluorine is this diatomic element. The other examples I give are for oxygen and chlorine. Let's look at chlorine first. Here, the only difference between the chlorine and the fluorine is that chlorine filled that second shell entirely because it's got 17 electrons after all. So it's 2 in the first, then 8, and then it's got 7. Here, this chlorine atom brought that electron into play. This chlorine atom brought that electron into play. They clicked together and formed a bond because each bond is made out of 2 electrons, like I said. What about situations where you're not 1 atom short of a full shell? Because the halogens are 1 atom short of a full shell. Fluorine's got 7 valence electrons. So does chlorine. What about the other ones? Well, they're all the same way. 1 atom, 1 electron short of a full shell. But oxygen behaves the same way as a diatomic element. Here's how that works. What happens is that an oxygen atom, valence electrons, it has 6 valence electrons. All of them do. So they can't just share 1 electron each, but it works if they share 2 electrons each. They're making what's called a double bond. In total, the covalently bonded electrons in this Bohr diagram for an oxygen molecule, there, 1, 2, 3, 4. This oxygen atom brought these 2 electrons to make covalent bonds. This one brought these 2. Collectively, we have 4 electrons involved in making covalent bonds. Each pair makes a bond. So 2 pairs makes 2 bonds. The atoms of oxygen are bonded covalently in a way that you've got 2 pairs of electrons making each bond between the oxygen atoms. In general, oxygen has this ability to form 2 covalent bonds. It can form it as what's called a double bond, sharing 2 pairs with another atom, or it can do it as 2 single bonds. When you get to, say, Chem 11, you're going to look at that. You're going to look at the behavior of oxygen and carbon and so on in making bonds and making molecules. And you're going to see the rule for oxygen, the rule for carbon. It makes 4 bonds. It can make a double bond and 2 single bonds, or 4 single bonds or 2 double bonds. Oxygen makes a double bond or 2 single bonds. Nitrogen is the same way. Nitrogen is right next to oxygen in the periodic table. In fact, it's between carbon and oxygen. Nitrogen, in fact, actually has to have 3 electrons it brings in. Each atom brings in 3 electrons to bond covalently. So you actually end up with what's called a triple bond. This explains why it's so terrifically difficult to rip apart nitrogen molecules. Nitrogen is N2 as a diatomic element. That's 3 covalent bonds, and so that's very tight as a chemical bond between the nitrogen atoms. So that's everything you need to know for this lesson. And you've looked at covalent network crystals and seen how they're found in rocks in nature as minerals. For example, diamond, for example, quartz, and you've looked at diatomic elements, and I've told you that you really will need to know those. They'll be very important in Science 10 and Chem 11 and more chemistry courses because they're involved in reactions all the time. I hope that this has been useful for you.